They're going to be, whoops, let's see this thing. There are going to be people that are going to be able to describe this a whole lot better than I will. But you can look it up. And the only reason why I know the things that I know is because I took digital electronics in school. And it was one of the few courses that I took that I fully retained a lot of what I learned in it. Um, Keep in mind that Minecraft has the necessary components to teach any kid digital electronics. You don't need breadboards. You don't need TTL circuits. You can do it all from within inside of Minecraft. You just have to learn how it works in Minecraft. And you can even describe how hardwired instructions work. You can describe a basic CPU component, probably. You can describe how an ALU works. You can show how pipelines, pipelines. The thing is, it's incredibly difficult. You have to put it in perspective. I mean, you could start it off in Minecraft and then end up using breadboards and then using PL, using GAL, PAL, programmable logic to create your own chips to put into your breadboard or your circuit, you know, your circuit card, and create your own solutions. That's kind of the idea of a Raspberry Pi computer is that you can create your own technologies using a full-fledged computer rather than having to create a piece of hardware. But there are things where pieces of the hardware with TTL circuits is going to be more advantageous, or things that use GALs or PALs, um, which are just these chips that have all these logic um, operations are arranged. Those things are going to be more suitable for some applications than a Raspberry Pi would be. And at least that's my assumption. All I learned about was the how to program a program a logic array, and with, by using using a kind of a source code that was similar to using something like C programming language to burn in the logic into these chips, and so that I wouldn't have to create a motherboard full of TTL circuits, which are just these circuits that have individual sets of logic gates on them, and you use these logic gates to create operations, microcoded operations. And so, if you wanted to create your own processor, you could do it with TTL circuits, but it would be very simple. It wouldn't. You couldn't do it to anything greater than maybe a than 4 bits or 8 bits. You couldn't get beyond that. And to do higher bit functions, you have to uh, have a full processor, or you have to have a lot of TTL circuits. And the problem with having TTL circuits is that they're incredibly inefficient. Though the electricity seems to not travel very far, the power doesn't travel very far. Um, any amount of length that you're using, if it is not on a very small scale, it's going to run fairly slowly. And so you want all these logic, and you want your clocks to be fast, and you want your operations to be very dense and on a small chip. Um, and even on that small chip, the length of the wires inside the chip, if you strung them out, would be much longer than you could imagine. It's just they're so dense, and they're so um, they're so well packed, and they're so thin. These circuits are so thin that um, they can store a room full of computing components into that chip, and the the more they've kind of reached the limit of what they can do in the amount of, and they, I mean, like the Intel processor company or people who create processors, they've kind of hit the limit of how dense you can tightly pack these circuits and create all the logic and stuff necessary to do operations. How that there are two kinds of processors out there. It's one called a reduced instruction set computer and a Cisc. There are probably others, but they're beyond my comprehension. A Cisc is a complex instruction computer, and what it does is it has a lot of operations in it for doing. It's kind of like having a multifunction scientific calculator. But if you look at a science calculator and you look at a regular calculator, you can tell there are a lot of operations there that you don't really know, that you really, you know, you'll probably never use. And that's the same idea. The Cisc would be the scientific calculator. The RISC would be your basic calculator, and then like a set of notepads with some pencils, you know. And so you know that you could do all of the operations that were on the scientific calculator using just simple math on that small calculator, and that would be the truth. But the problem is that you would spend a lot more time um, just creating the operations necessary to do what is on the Cis processor. But you have more time because on the Cis processor, it would take it longer than you had time to do on a regular calculator. So it sounds complex, but that's because I'm trying to make the analogy fit between a scientific calculator and a regular calculator. They both do the operations in the same amount of time, but the science calculator can do more than the regular calculator can. A reduced instruction set computer has fewer operations, and so it's like a regular calculator. A Cisc, a complex instruction computer, has lots of operations that it can do in the same amount of time as the other, but they do things like sine waveforms and tangential functions, sine functions, exponential functions, possibly even calculus integrals and things of that nature. Um, and my dad preferred reverse Polish notation. That's where you specify your operands, and then you specify your operation. So you would, to do 5 plus 3, you would do 5 3 plus, and to do 10 minus 5 plus 3, you would do 10, and then you do 5 3 plus minus. And so that what it would do is it would take the 5 3, add those together, and then subtract 10 by the result of 5 3. And that's reverse Polish notation. You could also do it the opposite way. You could go minus plus. I mean, there's a way that you could do it the opposite way, but people don't do that, and that's where you would say minus plus 5 3 10, or no, it'd be 10 5 3. So it'd be minus plus 10 5 3, and I don't know if you could really do that. I don't know how that's orchestrated, but I do know that the orientations of operations is dependent upon a tree of execution, and it's dependent on which child you look at first, and the parent is the operation. So the people out there that understand trees of evaluation would say, I know where you're trying to get at, and then they would probably go, that's really going to confuse a lot of people, and they say, well, I tried. The reduced instructions, so throw away all the shit that I just said, and just think that a reduced instruction set computer is one where any of the operations that you would ever need could be done theoretically. But in order to save time, the operations that you do a lot are hardwired to run in a single clock cycle. And in a clock cycle is the amount of time necessary to do a part of the operation, or the but if you hardwire it, you can do all the operation in one clock cycle. And in a reduced instruction set computer, it has all the space in the world to do certain operations in a single clock cycle, like divides and multiplies. Whereas in a Cisc processor, it would break up a divide and a multiply into a bunch of small operations that it would do using simpler hardwired instructions, and those are called microcode. And usually in a Cisc processor these days, or I don't know what point they did this, you could actually program some of the operations inside the processor to use combinations of microcoded operations. So things that would require math, some things would require just moving memory around, and whatever is needed to do with the operation. It's kind of like breaking up your division into a set of subtraction operations, and using the carries. And if you've ever done binary multiplication or division, it's similar to base 10 division. It's just that it's base 2, and anybody could work it out. But in a processor, since they use a lot of the computer for complex instructions, for big instructions, they cut down the amount of components that are necessary by creating the simple set of operations necessary to do all the parts of all the operations in the Cisc processor. It's like the Cisc processor's got a program for every single operation that you need to do, but it doesn't have all the components arranged to do all of those in a single clock cycle. So what it does is it uses an idea called a sequential circuit, where it does a sequence of operations, and they're timed. They're sequenced using a clock, and the clock determines what operation on the microcoded level is done to produce the necessary value for any operation that you're trying to perform, like a division or a multiplication. But in a Cisc processor, you use most of your space for operations and very little space for memory. You use it for operations and the programs, the microcoded instruction programs that use the basic components necessary to create any kind of operation. So it's like a bunch of instructions, a bunch of microcoded, a bunch of sub operations called that the microcode can use. It's organized in such a way that those processes are done um, are broken up over time, and the clock determines what operations. It's kind of like a recipe. First, you put in your eggs. First you do this, then you do this, then you do this, then you do this. That's a Cis processor. It's like the Cis processor has the entire cookbook of all of the recipes necessary to do very simple culinary things, and but you have limited kitchen space to do it on. In a reduced instruction set computer, you have lots of space to work in, but you have limited tools to do all those things necessary. So instead of getting a whisk, you just get a fork and a spoon. You don't get a whisk. You don't have you have a blender to blend stuff, but it's a certain kind of blender, not the one you use with your hand, but one that works in a bowl that you can set aside, and it does the entire operation by itself, possibly very much quicker than you could do it. And so that's a reduced instruction set computer. A reduced instruction set computer has some functions hardwired, and so that would be your automatic operations that get everything done without your involvement. And then it has some simple tools to do the basic things you need to do. And then you have all this memory, which would be all your kitchen space, to store away all of the necessary things that would go together to create whatever culinary product you're trying to create, whatever kind of food you're trying to create. And so you have more space, you have fewer tools, you have the same number of ingredients, but and you have tools that can perform most of the necessary operations super quick without your involvement. That's a reduced instruction set computer. A Cisc processor, you would have limited space. You would have all of the tools necessary to do anything you wanted to do, but on a limited kitchen space, and you wouldn't have all the things like the whisk. You would do the whisking. You wouldn't have a blender to do the whisk. You wouldn't have a mixer to do the whisking for you. And so, because you don't have the space to have that piece of equipment on your table, because you have a limited space on your table, but you can use any of the other tools to do that stuff much faster than you could using a fork or a spoon. And that's a Cis processor. And so you can do all the operations you need to do, but it takes longer. Or you could do a reduced instruction set where you don't have where some of the things you don't do a lot you have to do over time, but the things that you do a lot are simplified in such a way that they don't have to involve you in doing them. And that's the difference between a reduced instruction set computer and a complex instruction set computer. And in the 90s, IBM, Intel, and Motorola came together to create a processor called the PowerPc. And the idea behind it is it was a reduced instruction set computer. It was the basic components that were used in the Motorola processors and the Intel processors combined. So what they did was they figured, well, nobody's going to write the microcode necessary to switch between the Macintosh and the Windows system or whatever you're going to be using. So what we're going to do is create a computer that that can sandbox both different kinds of processors simply by using all the space in the world to have both computers working, both for doing the operations of a Macintosh as well as a Windows system. And so So the idea was just so that you could have a Macintosh and a Windows machine in the same computer. Um, it didn't really take off because it was seen as not performing up to par with the Intel processors, and it was suitable for the Motorola's because the Motorola's were much slower than the Intel processors and had been for a long time. Whenever Macintosh users switched from the Motorola's from the 6840s to the Intel um, Pentiums, they noticed a significant jump in the processing speed of the things that they were doing, and they thought Apple was lying to them all that time, and Apple was lying to them because Motorola didn't have the technology to do what Intel was doing, and Intel had streamlined a lot of the stuff that Motorola hadn't. And so Motorola fell behind Intel's production on creating faster processors. And so people on the PCs, even though the Macintosh users had developed a kind of a snooty disposition, that we're intellectuals and you're just stupid PC users. The PC users were like, you don't realize how slow your computer is. And they said, oh no, we're significant. We've got significant capabilities. And about the time of the late 90s, Apple wasn't able to keep the secrets from the people that were on the Macintosh. That some have found out that they're going to be more productive if they were on the PC platform. And they were asking Jobs to come in and fix this problem. And Jobs had already fixed the problem with his next computer by adopting the Intel processor line long before, well before Apple had even adopted it. And so all he did is he created a similar Macintosh operating system. I think this is above his next operating system. It kind of mixed the two together. And so when you're getting a Macintosh today, you're really not getting the same Macintosh that was debuted back in the 80s. You're getting basically a next computer with a Macintosh interface on top of it. And that runs many applications, whereas the next were a special flavor of computer, was not really meant to be used by the general population because it was meant to handle certain kinds of it had limited hardware components. It didn't support at the very beginning. It didn't support color. It had black and white, but high resolution screen, and they had implemented things in various ways, like that your graphics were WYSIWYG. What you see is what you get, because the windowing system was using PostScript, which is a language that your laser printer uses to draw the screen, and to draw to a laser printer was the same screen operations dumped to the printer. And so it was like it didn't have to translate pixels into geometry for the laser printer. It stored geometry kind of like in a flash animation. It stores it as lines and dots, and because of that, the resolution of your text and stuff was infinite. And so anyhow, the Next had a lot of features in it that a normal Macintosh didn't have in it. And whenever Jobs came in and fixed the Macintosh line, he introduced the Apple users to the Intel processor. They thought it was going to be inferior, but then they found out that it was superior to what they had been using, and a lot of them were flabbergasted, and started to realize that they were fools all that time. They were pissing on the PC users. They came to realization that the PC users actually had a leg up on them. It's just that their computers were just much harder to use. And that's really the thing that is that's what makes the Apple computers better, is that their components are more well thought out. It's just that the processors they had used from the beginning just didn't scale with time as well as the Intel processors. And so Intel had exceeded Motorola's capabilities in producing fast components. And Apple had no choice but to just keep their user base um, out of the know, just so that they could continue to sell their computers, because they knew that their market was made up of people who don't understand PCs and would not be able to adopt the PC platform. So they had a kind of a monopoly in a way, and it's people that preferred well-written programs, but are willing to do it on slower computers. And many wouldn't have to know anything better, because the kind of stuff they were doing didn't demand a whole lot of processor strength anyhow. And so um, when things shifted, the Apple users got a new perspective on the Intel processors. But the way every Apple computer is made, and the iPads and the iPhones are made, is that they're like a game console. All of the components that are necessary to do what is needed are included in that computer, and the configuration is well understood. It is not, most Macintoshes are not designed to be augmented, to be upgraded. And the modern PCs have lost the capacity to be upgraded the way the older PCs are, because modern PC users and modern Macintosh users are almost the same kind of person. They don't, even though they attest that they have the capacity to change their graphics processors in their computers, that's about the only thing they can change anymore. The sound processors, the networking hardware, and all that stuff is included in the motherboard. And you can see this if you ever look in a Windows machine today and look at a Windows machine from like 10 or 20 years ago. You will see that the modern PC is just a very small, it's a small motherboard about this big. You know, it's like about that big. And it has a place for a graphics card, but that's all there is. You can't put in modems, and it doesn't make any sense to have a modem or an Ethernet card in there whenever all that stuff can be put into the um, okay. And so that's that, and I have to cut it there. So